Section 13.3 is on geometric probability. Geometric probability is defined as a probability involving geometric measure such as length or area. The length probability ratio says that if a line segment contains another segment and a point on the first segment is chosen at random, then the probability that the point is on the second segment is the length of the second segment divided by the length of the first segment. That sounds really wordy. Let's take a look at a couple examples. It's actually a lot simpler than it sounds. So, for example, point X is chosen at random on segment JM. Find each probability. So here we have segment JM, and we know that JK is 3 units long, KL is 7 units long, and LM is 4 units long. So now first of all, we need to find the probability that point X chosen at random lies on segment LM. So to do that, we're going to take the length of segment LM and divide that by the length of segment JM. So LM is 4, JM is 3 plus 7 plus 4, or 14, reducing that fraction 2 over 7. So the probability that just choosing a point at random on JM, the probability of that being on segment LM is 2/7. Second example, what is the probability that point X chosen at random lies on segment JL? Well, that's going to be the length of JL over the length of the entire segment JM. JL is 10, JM is 14, and that fraction reduces to 5/7. Here's another example. Halley's Comet orbits the Earth every 76 years. What is the probability that it will orbit the Earth in the next decade? So the probability that it will orbit the Earth in the next decade is, and the next decade is 10 years long, so in the next 10 years, and it does it every 76 years, reducing that fraction, that's 5 over 38. So remember, the idea of probability is what I want over what's possible. I want it to be in the next decade, but it only happens every 76 years. The area probability ratio says that if a region A contains a region B and a point E in region A is chosen at random, then the probability that point E lies in region B is the area of region B divided by the area of region A. Let's take a look at an example of that. So the targets of a dartboard are formed by 3 concentric circles, and I don't draw circles very well. Let's just imagine those are circles. If the diameter of the center circle is 4 inches and the circles are spread 3 inches apart, what is the probability that a player will throw a dart into the center circle? Okay, so these are concentric, they all have the same center, and the center circle is the diameter of that is 4 inches, so that means that its radius, this right here, is 2 inches. And then we know that the circles are spread 3 inches apart, so this would be 3 inches, and this is also going to be 3 inches. So let's say the radius of the large circle is going to be 2 plus 3 plus 3, or 8 inches. And the radius of the center circle is 2 inches. So the probability that the dart will land in the center circle is going to be the area of the center circle divided by the area of the large circle. So the area of the center circle is, remember, area is pi r squared, so the radius is 2, so 2 squared is 4, so 4 pi times the radius squared. The area of the large circle is going to be also pi times the radius squared, or pi times 8 squared, or 64 squared. Reducing that, my pi's will cancel, and 4 goes into 64 16 times. So the probability of the dart landing in the center circle is 1 out of 16. So here's a spinner with 5 spaces on it, each representing a different sector of varying degrees of measure. So what is the probability that if the spinner is spun at random, that it will land on section 2? Section 2 has an arc measure of 58 degrees, and we know that the total number of degrees in a circle is 360. Reducing that fraction is 29 over 180. So that's the probability of the spinner landing on section 2. The probability of the spinner landing on section 5 is going to be 109, because that's the arc measure of the segment that is section 5 over 360, and that fraction can't be reduced. So to sum up this section, we can talk about probability with regard to area using the area probability ratio, and we can talk about probability with regard to segment length, and all of this falls under the category of geometric probability.